Okay, we've been teasing continuity for a long time, and if you guessed that the next video of differentiability and continuity was continuity, you guessed correctly. We're finally going to talk about what it means to be continuous. And there are some really fancy definitions about continuity. We're going to stick to some simple, relatively informal ones, okay? So again, like a couple things in this class, we're going to have another informal definition. So F is continuous. And again, a lot of times I'm going to abbreviate continuous as just CTS. At a point, just like differentiability, we're going to talk about at a specific point if there are no jumps or gaps or holes at x equals a. All right, more formally, but still not super duper formal is, another way to look about that is that the limit as x approaches a of that function is equal to the function value. So remember back to our limit properties. We had a couple limit properties and we skipped a couple more. And we said, if it's a rational function, then to evaluate a limit, you can just look at the function value. We said that was true. That was a property for rational functions. That's because rational functions are continuous everywhere where the denominator is not equal to 0. Okay? And that's why that property worked that way. So now we're kind of looking at the other direction of that property. In fact, that's the definition of continuity. One definition of continuity. There's some really cool definitions of continuity with Greek letters. You should Google it or let me know if you're curious about it. I'm sure you'll love it. All right. Let's look at some examples. Okay. Look at some things that are continuous, some things that are not continuous. And let's check this out. All right. Say we have a function like this, and it goes up like a line, and then it's jagged, and then jagged again, and then it goes like that. So this function's continuous everywhere. Another way to think of continuity is, can I graph the whole function without lifting up my pen or my pencil? Okay, so everywhere, there's no gaps, there's no jumps, there's no holes. It's kind of weird looking, and we would say that it's not differentiable at these places, but it is continuous. It is a continuous curly, whirly, jaggedy doodah. All right, that's the fancy mathematical definition. All right, so this is actually continuous everywhere. All right, we can look at another one. Don't worry, I'll eventually give you one that is not continuous everywhere. Let's look at a function that looks like this. That has an open circle up here. So kind of like two halves of a parabola. This one is continuous almost everywhere. Right? This whole region, it's continuous all here, right? There's no jumps, holes, there's no gaps. It's continuous in this entire area as well, but it's not continuous right here. It jumps. You cannot connect these two things without lifting up your pencil. All right, so if we call this point, this x coordinate A, we'd say it's not continuous at x equals a. But again, it's continuous literally everywhere else. All right, so these are just some examples. I'll give you some more examples. This next one is a pretty famous function. If you haven't heard of this upcoming function, then you need to change what TV programs you're watching and watch more function TV show, yeah, or whatever. So this next one goes over here. It's flat, and then it goes like this. Still flat. Goes like this. Still flat. Goes like this. Still flat. This is what's informally known as the step function, and it kind of keeps on doing that forever. Really hard to do dashed lines like this, or dotted lines. This is not continuous. In fact, it's not continuous at every integer value. So it's not continuous at 1, 2, 3, 4, etc. All right, it looks like a watt, but it's a not, I promise. They're not continuous at x is equal to 1, 2, 3, etc. But it is continuous everywhere else. So if you imagine this graph kind of goes on forever in both directions, then it would be not continuous at an infinite number of places, and it would be continuous at an infinite number of places as well. So it's kind of a little strange. And then the last example I want to give you, something like this. Again, this is almost continuous everywhere, but still at this x coordinate right here, it's not continuous there. One of the definitions that we had for continuity, let's go back to it. Does the limit at the point equal the function value at that point? And you can see here the limit is actually this y coordinate right here. But the function value is way up here. So the limit is not the same thing as the function value in this case. So it's not continuous at x is equal to a. All right. Again, continuous at an infinite number of places. It's the only one place that it's not continuous at. All right. So those are some examples. Let's get into something kind of like your homework problems, shall we? Example 2. Is f continuous at x equals 1? And I'll give you this function. We got a nice piecewise function here. Hope you're ready for it. It has the piece x minus 1. For 0 is between, x is between 0 and 1. We use the piece just 1 when x is equal to 1. We use the piece 2x minus 2 when x is greater than 1. So again, we're going to do this by graphing. There are other ways of doing it without graphing, but graphing is good for 2 reasons. 1, I think it makes the problem a lot easier to solve, and 2, it's good practice for graphing piecewise functions. And again, a lot of students can struggle with piecewise functions, so the more practice you get, the more you will not struggle with it. Like lifting weights over here, okay? I know you don't want to bench press this amount, but we'll do it, and it'll get easier as time goes on. But don't worry, you got some people spotting for you. I actually hate lifting weights, and I've only done it for very small portions of my life. So let's get graphing. All right, so we're going to go over here. And, oh, that's like right below the line. All right, don't worry about it. So when x is between 0 and 1, we're on this line. This is the line with slope 1. It's 1x. And y-intercept, -1. So it has slope 1. So this line kind of looks like this. But remember, we don't want the whole line. This is a piecewise function. We only want this portion of the line when x is between 0 and 1. So everywhere outside of 0 and 1, we're erasing. This is only from when x is equal to 0 up to x equals 1. We got the line right here. And now we have to think open circles, closed circles. Again, open circle is when the thing is not included. Closed circle is when it is. It'll be a closed circle when x is equal to 0. And it's going to be an open circle when x is equal to 1. We'll have an open circle here, a really big open circle apparently. And that's the first piece. That's our first piece of this piecewise function. Next piece. When x is equal to 1, y is equal to 1. That's just a point. I don't even need to finish graphing this. I'm going to finish graphing it, but you already know the answer. Is this function continuous? No, that's a hole. That's a jump. Danger. this is no good. Let's keep going just for practice. All right, so the next one is 2x minus 2. Means it has the, I'm going to use this in a different color. No, I won't. So line 2x minus 2 means y-intercept of negative 2. Slope of positive 2. So it looks something like this. But again, it's a piecewise function. This is only for x is greater than 1. We're going to erase everywhere not greater than 1. So we're still going to have an open circle here, right? We still have an open circle here because 1 is not included right there. We have 3 pieces. We have the first piece, that's this line. We have the second piece, that's that point. And we have the third piece that goes on forever after. So not continuous. It's close. It's almost continuous. If this dot just got moved down a little bit, then it'd be continuous, but it's not. There's a hole. Our answer is just going to be a big, fat no. There we go. Very enthusiastic answer, because we are very enthusiastic about math. At least some of us are. At least one of us is. All right, not continuous. All right, let's go on to the last example, shall we? Example 3. So I'm actually going to bring out the text here because it is a little long. So the function below is is defined for all x except x equals 4. Define the function at this point to make f of x continuous for all x. All right, and in this case, the function is f of x is equal to x squared plus x minus 12 divided by x plus 4. And again, x is not. Hey, can you stop going down there, line? X is everything except for negative 4. Whew. Jason, in the case of the missing negatives. So let's look at this graphically, what's going on. Because as it's written, it's a little confusing. But if you think about it graphically, it makes a lot more sense. So this is a function that's defined everywhere except for at negative 4. All right. So we want to sort of turn this into a piecewise function. All right, so let's turn this into a piecewise function and just see, just like that last problem, what does this piece have to be to make it continuous? So in the last one, right, if we looked over here and changed this to a 0, then the function's continuous. That's what this next problem is asking, is what do we have to have at this point to make it continuous? Well, let's visualize it. This is what the function looks like. It doesn't look like it'd be a line, right? It looks like it's more complicated than a line, but it really is. It's a line everywhere except for at negative 4, where we have a hole. So it's not continuous because there's a hole. But if we could fill in the hole, then it'd be continuous. So where's this hole at? This hole's at negative 4, negative 7. So that's going to be what guides our answer. Is if we said, okay, well, let's just fill in this hole. Well, now it's continuous. That's all there is to it. So graphically, that's how you do it. But let's still look analytically at how you solve this. And to do it analytically, you remember limits, right? It's continuous if the limit as x approaches 4 of f of x equals f of 4. All right, this is, sorry, negative 4 Woo! These negatives, man. It's missing up here too. Oh no. All right. Negatives are disappearing all over the place. All right. So let's look at this left-hand side. What does the limit look like? What is the limit here? The limit as x approaches -4 of x squared plus x minus 12 over x plus 4. And you, being the astute and excellent math students, are going to say, I remember our limit properties. This is a rational function, a quadratic divided by a quadratic. Rational functions are continuous everywhere, except for when the denominator is equal to 0. So we can just plug in -4. But again, if you plug in -4, you're going to get a divide by 0 error. That's no good. So how did we do it when we couldn't plug in? We'd simplify, okay? So here we're going to simplify by factoring. We're going to get the limit as x approaches -4. The top is a trinomial, which means that if it can factor, it's going to factor like this. So the first one's a positive, but they're different signs. Remember, this always tells you what the sign of the first binomial is. And this says they have to be different. If this were a plus, that'd mean they were the same. So one's a plus, one's a minus. We have an x squared term, which means this is an x and this is an x. We need something that multiplies to -12, that adds to +1. We need +4 minus 3. And we get cancellation. So now we can just evaluate the limit, plug in the -4, and you're going to get -7. All right, which doesn't really fit here. Well, go on to the next page. So we said the limit is -7. It's continuous if the limit equals the function value. So all we need to do is say, well, if f of -4 is -7, then we have continuity. That's what we're going to do. We're going to say f of x is equal to -4 to -7 if x is equal to -4. Otherwise, it's going to equal the original thing that we had before. I believe was that. For x not equal to -4. Let me just double check that that is the same function. X squared plus x minus 12 over x plus 4. And now this is continuous for all x. So we've turned something into a piecewise function. And we've made it continuous, right? Before, it was not continuous. It looked like this. But what we did is turned it into a piecewise function, so it looks like this. And this right here is a darn good continuous function. Bona fide continuous, all right? We filled it in. We made it continuous. This is actually something that happens in a lot more generality in math in general. We have like functions or we have things that don't behave the way that we want them to. So we will embed them in a way that actually gives them additional characteristics that make them better to work with. This is a very, very common thing that we do in math. Anyway, that's this here. Hope you enjoyed mathematics. That's my goal for this class, right? I want you to learn, but I also want you to at least like some of this stuff. There's some cool stuff in math. All right, go ahead and work through the problems, and please don't hesitate to ask me if you have any questions.